Alright, so a little bit of background on Platonic solids before we start here. Platonic solids are named after the Greek Plato, deriving from his work in around 350 BCE, Timaeus. As time went on, expanding on Plato's work with Platonic solids was Archimedes, who developed his own Archimedean solids, which is just allowing more than one type of shape or two different types of faces to make up a shape. For example, the book uses a soccer ball. Pappus also developed some work, especially in relation to Archimedes, and work continues on to this day. So, for example, semi-recently, in 1852, Ludwig Schläfli proved the existence of exactly 6 regular Platonic solids in 4D space. One of these is a hypercube, which I'll show you here. There are 3 Platonic solids in 5D space, and there are exactly 3 in all higher dimensions above 5. One kind of interesting thing about the way history of math works is Schläfli actually didn't get his work published until he died, where it was published in 1901. So before we start getting to the actual Platonic solids themselves, let's go over some of the terms that make up what makes up a Platonic solid. So first we'll go over the definition of regular in math. So a regular shape in this case means that this shape has all sides equal and all angles within that shape equal. So for example, we have a square here. Each corner of a square is 90 degrees, and each side of the square is going to be the equal x. Moving on from that, we have congruence. Congruence in math means 2 or more entities are equal. So for a small example, x is congruent to y if and only if x equals y. So in the case of geometry, one shape is congruent to another shape if all of their sides are equal and all the angles inside them are also equal. The next term is convex, literally meaning to curve outward, or in the case of straight-sided polygons, meaning no internal angle is greater than 180 degrees. So essentially what that means, if you look at the examples there, for straight-sided polygons, as long as there's no intrusion or dent or penetration in the line, it's one solid straight line surrounding the entire object, then it is convex. So for the Platonic solids, they're all convex, regular polygons. In general, there are 5 Platonic solids. There's the tetrahedron with 4 faces, the hexahedron with 6 faces, octahedron with 8 faces, dodecahedron with 12 faces, and icosahedron with 20 faces. Alright, so a burning question you might have is why there are only 5 Platonic solids. Well, there are only 5 in 3 dimensions, the one we use to visualize. So first let's get low and look at a 2D universe and see how this applies there. So in 2D there's actually no boundaries regarding vertexes, the same constrictions that there are with 3D in 2 dimensions. In 2 dimensions it only concerns a single regular polygon itself, and as it turns out, if we apply the Platonic definitions to that, regular, convex, congruent, there are actually infinitely many variations of the solid in 2D space. So in the little illustration I have here, obviously one line isn't going to do anything, and neither is 2, but once we get to 3, we have an equilateral triangle, 4 is a square, and so on, and we can actually go up to infinity, the n-sided polygon, but a circle is not a Platonic solid, and I'll get to that again in 3 dimensions. So what constricts the 3rd dimension to 5 Platonic solids? Well, if we evaluate 3D polygons, since the polygons consist of congruent faces, each vertex is exactly alike, and therefore we only have to look at one single vertex in these 3-dimensional polygons, and we can apply that same vertex to literally every one, because if it's a regular, Platonic solid, each vertex situation is the same as every other one. So what are the rules for that? So in order to make a proper vertex for the Platonic solids, the faces of the polygon meeting at that vertex must be less than 360 degrees. If a vertex is greater than or equal to 360 degrees, the vertex doesn't create a joint for the faces of this polygon to fold. It would just create a flat surface. On the bottom, I have a few examples here for equilateral triangles. Those have 60 degrees, and we can add those up to 5 times for 300 degrees for a maximum amount of summations before we hit the 360 degree mark and create a flat surface. And so from the variations 3, 4, and 5, that's how we get the 3D Platonic solids of the tetrahedron, the octahedron, and the icosahedron. For squares in sequence of 90 degrees, you can get up to 270 degrees, but 90 more than that is 360 and creates a flat surface. And the same thing with pentagons. Each angle is 108 degrees, and you can only get up to 324 degrees without going over 360. So again, why are there only 5 Platonic solids? All right, so let's move up to the 6-sided polygon. We got a hexagon here, and this is going to prove why we can't have anything above a pentagon be included in the 3D Platonic solids. For hexagons, a regular hexagon has angles of 120 degrees. So you can add 2 hexagons to get 240 degrees, but those 2 hexagons aren't enough to, in the 3-dimensional universe, fold up and create a regular polygon. And once you add another 120 degree angle to it, you get 360 degrees. So these 3 hexagons aren't going to be able to fold into a 3-dimensional shape, they actually just create a flat surface. So for heptagons and onwards, each regular angle measures over 120 degrees, and therefore, because each angle is more than 120 degrees, and we already proved that in a hexagonal case, it's going to equal 360 degrees and create a flat surface. Consequently, every incremental polygon is also going to be 360 degrees or greater, and therefore, there are only 5 Platonic solids. And interestingly enough, this is also the last proposition proved in the famous Greek mathematician Euclid's Elements. And Euclid is kind of the base for geometry, to the point where we split geometry into Euclidean geometry and non-Euclidean geometry. And lastly, the reason that spheres in a 3-dimensional universe are not considered a Platonic solid is because the face of the spheres measure 0. On a perfect sphere, there is literally no face. So the moment we have any incremental amount of a face, that is when we can allow for this to be a Platonic solid. But in the case of 3-dimensional objects, obviously, nothing above a pentagon can actually create a 3D surface like that. So it only applies to the 2D universe, where this single face can have infinitely many segments making up its regular shape, but the moment it hits that perfect circle, or in the 3-dimensional universe a perfect sphere, those faces inherently just don't exist anymore.